How do chemical reactions happen? In a chemical reaction, atoms from different molecules interact with each other. These atoms break their bonds and form new ones. Energy is usually involved in these processes. Some reactions release energy, while others need energy to happen. A simple example of a chemical reaction is the reaction between hydrogen H and oxygen O to form water HO. When hydrogen and oxygen react, they form water and release energy in the process. Chapter 8. The importance of understanding atoms and molecules. Is it important to understand atoms, molecules, compounds, and mixtures? Understanding these tiny particles helps us in many areas of science and everyday life. Here are just a few reasons why this knowledge is so important. 1. Medicine scientists use their knowledge of atoms and molecules to create new medicines. By understanding how different molecules interact in the body, scientists can design drugs that help treat diseases. 2. Environmental science. Atoms and molecules also play a huge role in environmental science. Understanding how different gases like carbon dioxide (CO) and methane (CH) affect the environment can help us fight climate change. 3. Technology. The technology we use, from smartphones to computers, is built on understanding atoms and molecules. Engineers design materials and electronics by knowing how atoms interact with each other. Chapter 9. Atomic theory and the scientists who shaped our understanding. Through history, scientists have spent a lot of time trying to figure out what atoms are and how they work. The understanding of atoms and molecules has evolved over time, and many brilliant scientists have contributed to this knowledge. The beginnings of atomic theory. The idea of the atom goes back thousands of years to ancient Greece. A philosopher named Democritus is often credited with being one of the first people to suggest that everything is made of tiny, indivisible particles, which he called atoms. He imagined that if you kept cutting a piece of matter into smaller and smaller pieces, eventually you would reach a point where it couldn't be cut anymore. This was the beginning of the idea of the atom, but it wasn't until much later that scientists could prove it. John Dalton and the first atomic model. In the early 1800s, John Dalton, an English chemist, proposed the first modern theory of the atom. He suggested that atoms are indivisible particles that combine to form compounds in fixed ratios. His atomic theory laid the groundwork for understanding how different elements react with each other. Dalton's model of the atom was very simple. He imagined the atom as a tiny, solid sphere, like a billiard ball. He also believed that each element's atoms were all identical to each other, but different from the atoms of other elements. J. Thomson and the discovery of electrons. In the late 1800s, a scientist named J. Thomson made a groundbreaking discovery. While experimenting with cathode ray streams of electrons, he found that atoms weren't indivisible after all. Instead, atoms were made up of smaller particles, including negatively charged particles called electrons. Thomson's discovery led to a new model of the atom, often called the plum pudding model. In this model, the atom was imagined as a ball of positive charge with electrons scattered throughout it, like raisins in a plum pudding. Ernest Rutherford and the nucleus. In 1911, a scientist named Ernest Rutherford made another important discovery. Through his famous gold foil experiment, he found that the atom had a small, dense, positively charged center, which he called the nucleus. He also discovered that most of the atom was made up of empty space. This completely changed how scientists viewed the atom. Rutherford's discovery of the nucleus led to the creation of the nuclear model of the atom, where electrons move around a central nucleus. Niels Bohr and the electron orbits. In 1913, the Danish scientist Niels Bohr built on Rutherford's work and proposed a new model of the atom. Bohr suggested that electrons travel around the nucleus in specific orbits or energy levels. His model showed that electrons could jump from one energy level to another, and these jumps were important in explaining how atoms absorb and release energy. This model helped explain the behavior of atoms and was an important step toward our modern understanding of the atom. Modern atomic theory. Quantum mechanics. In the 20th century, scientists like Werner Heisenberg and Erwin Schrödinger developed a new understanding of the atom based on quantum mechanics, a branch of physics that deals with the behavior of very tiny particles. Quantum mechanics describes electrons as existing in regions of probability, rather than fixed orbits. This theory also introduced the concept of electron clouds, where electrons are likely to be found, rather than specific paths. Quantum mechanics has led to many important discoveries in science and technology, including the development of computers, lasers, and medical imaging techniques. Chapter 10. The periodic table and element organization. Now that we know about atoms and their structure, let's explore how elements are organized. The periodic table is a chart that arranges all the known elements in a specific order based on their properties. Each element has a unique number of protons, called the atomic number, which determines the element's identity. What is the periodic table? The periodic table is like a map for scientists. It helps them understand the relationships between different elements and predict how they will behave in chemical reactions. The table is organized into rows called periods and columns called groups. Periods. The rows of the periodic table are called periods. Elements in the same period have the same number of electron shells or energy levels. Groups. The columns of the periodic table are called groups or families. Elements in the same group share similar chemical properties because they have the same number of electrons in their outermost shell. For example, elements in group 1 like lithium, sodium, and potassium are all metals that react quickly with water. Elements in group 18 like helium, neon, and argon are noble gases, which are very stable and don't react with other elements easily. Key groups in the periodic table: alkali metals group 1. These are highly reactive metals like lithium Li, sodium Na, and potassium K. They are soft and can be cut with a knife. Noble gases group 18. These gases, like helium He, neon Ni, and argon R, don't easily form compounds because they already have full electron shells. Halogens group 17. These elements, like chlorine Cl and fluorine F, are highly reactive and often form salts when combined with metals. Chapter 11. The role of atoms, molecules, and compounds in everyday life. Now that we've learned about the science behind atoms, molecules, compounds, and mixtures, let's look at how this knowledge affects our daily lives. From the food we eat to the technology we use, understanding atoms and molecules helps us in countless ways. Food and nutrition. The food you eat is made up of molecules and compounds. For example, carbohydrates, fats, and proteins are all different types of molecules that your body uses for energy and growth. The process of digestion involves breaking down large molecules like starches and proteins into smaller molecules that can be absorbed by your body. Water, which is made of hydrogen and oxygen atoms, is also essential for life because it helps carry nutrients and regulate temperature in your body. Medicine and health. In medicine, understanding the way atoms and molecules interact is crucial. Scientists design medicines by knowing how certain molecules will interact with the atoms in our bodies. For example, aspirin is a molecule that helps relieve pain by interacting with certain parts of your body's cells. Similarly, vaccines are made up of molecules that help train your body's immune system to fight off diseases. Energy production. Atoms and molecules are also involved in producing energy. In power plants, atoms are rearranged to release energy in the form of heat or electricity. For example, in a nuclear power plant, atoms of uranium are split apart in a process called nuclear fission, which releases energy. This energy can be used to produce electricity to power homes and businesses. Technology and electronics. The technology we use every day, like smartphones, computers, and televisions, is based on the behavior of atoms and molecules. Semiconductors, which are materials used in electronic devices, are made of atoms that have been carefully arranged to control the flow of electricity. The tiny transistors inside your phone or computer are made of semiconductors and help process information at incredible speeds. Chapter 12. The future of atomic science. As science continues to advance, our understanding of atoms and molecules will only grow. Scientists are constantly discovering new elements, and they are learning more about how atoms can be manipulated for useful purposes. For example, in the field of nanotechnology, scientists are working to create tiny machines made of atoms that could be used for medical treatments, environmental cleanup, or even space exploration. Quantum computing. One of the most exciting areas of atomic science is quantum computing. Traditional computers use bits to store information, but quantum computers use quantum bits qubits, which can exist in multiple states at once. This allows quantum computers to process information much faster than classical computers. Quantum computers could revolutionize everything from medicine to artificial intelligence. Nuclear fusion and clean energy. Another exciting field is nuclear fusion, the process by which atoms are fused together to release energy. If scientists can develop nuclear fusion as a reliable energy source, it could provide an almost unlimited supply of clean energy, which could help solve the world's energy problems. Conclusion: the tiny world that shapes our big world, atoms, molecules, and the wonders of the universe. Have learned a lot about the tiny building blocks of the universe: atoms, molecules, compounds, and mixtures. These tiny particles make up everything in the world, and understanding them has led to amazing discoveries in science, medicine, technology, and more. From the air we breathe to the devices we use, atoms and molecules are the key to understanding how the world works. As science continues to advance, our knowledge of atoms and molecules will continue to grow, leading to new discoveries that can help improve our lives and solve the challenges of the future. The tiny world of atoms is full of wonders, and by studying it, we can unlock the secrets of the universe. Atoms, molecules, compounds, and mixtures are all around us, shaping everything in the world. The tiny particles that make up everything are constantly moving, interacting, and combining in different ways. By studying these tiny building blocks, we learn how the world works and how we can make it better. Whether we are creating new medicines, developing new technologies, or protecting the environment, the science of tiny particles plays a huge role in our lives. The next time you look around, remember, everything you see is made of atoms, molecules, and compounds, hidden and fascinating forces that work together to make the world we know.
Later scientists followed suit. Atoms would remain all but forgotten until 1808, when a Quaker teacher named John Dalton sought to challenge Aristotelian theory. Whereas Democritus's atomism had been purely theoretical, Dalton showed that common substances always broke down into the same elements in the same proportions. He concluded that the various compounds were combinations of atoms of different elements, each of a particular size and mass, that could neither be created nor destroyed. Though he received many honors for his work, as a Quaker, Dalton lived modestly until the end of his days. Atomic theory was now accepted by the scientific community, but the next major advancement would not come until nearly a century later, with the physicist J.J. Thomson's 1897 discovery of the electron. In what we might call the chocolate chip cookie model of the atom, he showed atoms as uniformly packed spheres of positive matter, filled with negatively charged electrons. Thomson won a Nobel Prize in 1906 for his electron discovery, but his model of the atom didn't stick around long. This was because he happened to have some pretty smart students, including a certain Ernest Rutherford, who would become known as the father of the nuclear age. While studying the effects of X-rays on gases, Rutherford decided to investigate atoms more closely by shooting small, positively charged alpha particles at a sheet of gold foil. Under Thomson's model, the atom's thinly dispersed positive charge would not be enough to deflect the particles in any one place. The effect would have been like a bunch of tennis balls punching through a thin paper screen. But while most of the particles did pass through, some bounced right back, suggesting that the foil was more like a thick net with a very large mesh. Rutherford concluded that atoms consisted largely of empty space, with just a few electrons, while most of the mass was concentrated in the center, which he termed the nucleus. The alpha particles passed through the gaps, but bounced back from the dense, positively charged nucleus. But the atomic theory wasn't complete just yet. In 1913, another of Thomson's students by the name of Niels Bohr expanded on Rutherford's nuclear model. Drawing on earlier work by Max Planck and Albert Einstein, he stipulated that electrons orbit the nucleus at fixed energies and distances, able to jump from one level to another, but not to exist in the space between. Bohr's planetary model took center stage, but soon it too encountered some complications. Experiments had shown that rather than simply being discrete particles, electrons simultaneously behaved like waves, not being confined to a particular point in space. And in formulating his famous uncertainty principle, Werner Heisenberg showed it was impossible to determine both the exact position and speed of electrons as they moved around an atom. The idea that electrons cannot be pinpointed but exist within a range of possible locations gave rise to the current quantum model of the atom, a fascinating theory with a whole new set of complexities whose implications have yet to be fully grasped. Even though our understanding of atoms keeps changing, the basic fact of atoms remains. So let's celebrate the triumph of atomic theory with some fireworks. As electrons circling an atom shift between energy levels, they absorb or release energy in the form of specific wavelengths of light, resulting in all the marvelous colors we see. And we can imagine Democritus watching from somewhere, satisfied that over 2 millennia later, he turned out to have been right all along.
Everything is made of atoms. Yes, even you. Atoms consist of a core and some electrons. The core is made of protons and neutrons, and depending on the number of protons, you get different elements. Water is made of hydrogen and oxygen. This is some sodium. I wonder what happens when you... Oopsie. Quantum mechanics tells us that this is not what atoms actually look like. They look more like this, but we'll get to that later. For now, just think of atoms as having multiple electron shells. The electrons in the outermost shell are called valence electrons. Most of chemistry is really just the behavior of these electrons. Every element is listed in the periodic table. All elements in the same column or group have the same number of valence electrons. For the main groups, the number of valence electrons is just the group number from 1 to 8. Except for helium. It's too small to have 8 electrons, it can only have 2, but still, it acts like a noble gas, so it's just kind of grouped in with those. Luckily, the transition metals also follow a nice pattern. That was a lie, it's kind of a mess, but that's not so important for now, so we'll get to that later. Elements with the same number of valence electrons tend to show similar behavior in chemical reactions. For example, the first group without hydrogen is called the alkali metals. Here's some things they have in common. They have 1 valence electron, they're shiny metals, they're kind of soft, and they do this sometimes. All elements in the same row or period have the same number of shells. This number increases from top to bottom. Also, the mass gets bigger from left to right as each element gains a proton, an electron, and some neutrons. Depending on the number of neutrons in the core, you get different isotopes of the same element, most of which are pretty unstable and fall apart, releasing ionizing radiation. Fun fact, that stuff will kill you. If an atom has the same amount of electrons as protons, it has no charge. If it has more, it has a negative charge, and if it has less, it has a positive charge. Charged atoms are called ions. Negative ions are anions, and positive ions are cations. The periodic table is also pretty much a dictionary, as every cell tells you the name and symbol of an element, the number of protons in the core, which is also the total number of electrons, and the atomic mass, which is the mass of neutrons and protons combined. The periodic table is roughly divided into 3 categories. Left of this line are the metals, right of it are the non-metals, which are mostly gases, and the line is called the semi-metals, which have properties that fall somewhere in between. 2 or more atoms bonded together form a molecule. If you have at least 2 different elements, you get a compound. Oh yeah, this is probably a good time to mention that compounds often behave completely differently than the elements they're made of. Like, put together an explosive metal and a toxic gas, and you get, of course, an even more table salt. You get table salt. There's many ways to write molecules, for example the molecular formula, where you just count the number of each atom in a molecule and write them as a subscript number next to the element symbol. But that has some problems. Look at these 2 molecules. They have the same molecular formula, but obviously they're not the same. They're isomers. Showing this difference is probably kind of important. It's the only thing that separates graphite from diamonds, because they're both just fancy versions of carbon, and I don't think anyone's gonna go, yes, this dusty black blob is indeed very expensive. One way to show the structure of an atom is the Lewis dot structure, which represents the valence electrons and bonds as dots and lines. This is also going to help us understand why atoms bond in the first place. You see, everything in the universe wants to get to a state of lower energy. That's why a ball on a hill will roll down by itself, because that decreases its potential energy. This trend also applies to atoms. The state of lowest potential energy is having a full outer shell of electrons, which is most often 8, or in the case of hydrogen and helium, 2. If you think back to the periodic table, you'll see that all noble gases already have a full outer shell, which is why they don't really want to react with anything. If two atoms don't have a full outer shell but can achieve one by sharing electrons, they will naturally do so, the same way a ball will go downhill, as their combined energy would be lower than if they were separate. The sharing of electrons is called a covalent bond. These bonds are also caused by the positively charged nucleus of an atom tugging on electrons of another atom. The strength of this pull is called electronegativity. In the periodic table, the electronegativity increases from bottom left to the top right. Therefore, fluorine has the strongest pull. It's just unbelievably desperate for an electron. If the difference in electronegativity is bigger than about 1.7, you get an ionic bond. A good example is sodium chloride. Chlorine would do anything for an electron, while sodium has one too many and just kinda wants to get rid of it anyway. Perfect, they both say, forming an ionic bond, where sodium loses an electron and turns into a cation, and chlorine gains an electron and turns into an anion. That seems pretty important. You might want to remember it. The most common place you see ionic bonds is in salt. Yes, also table salt, but more generally, when metals and nonmetals bond, you get a salt, which is just a grid of ions. Speaking of metals, a pure metal forms metallic bonds. You can imagine this as a huge grid of positively charged nuclei which are surrounded by freely moving electrons. You see, in a metal grid, the valence electrons are kinda promiscuous, or as the nerds call it, delocalized. They can move freely in a giant playground of nuclei instead of being loyal to just one. This kind of bond is responsible for the properties of metals, like conducting electricity and heat, and also being malleable, as in being kind of bendy. Like, you can hammer on this stuff until it's the most deformed, unelegant, and ugly-looking piece of material ever known, and it will just limp along as if nothing ever happened. If the difference in electronegativity is lower than about 0.5, the electrons are shared pretty equally and you get a nonpolar covalent bond. If it's bigger than 0.5 but smaller than around 1.7, one of the elements is pulling on the electrons pretty hard. Not quite hard enough to completely steal an electron, but definitely hard enough to skew the electrons a bit, making it a polar covalent bond. An example is water. Oxygen has a very high electronegativity compared to hydrogen. As a result, it pulls the electrons of hydrogen so hard that they kind of belong to oxygen, giving it a partial negative charge and leaving hydrogen with a partial positive charge. The presence of two poles with opposite charge is called an electric dipole. All permanent dipole molecules can interact with each other, and really with anything that has a charge. As a result, the molecules will tug on each other and arrange themselves in a way that oppositely charged ends are next to each other. The forces acting between them are called intermolecular forces, or IMFs. A specific example is hydrogen bonds, where hydrogen bonds to something very electronegative, like fluorine, oxygen, or nitrogen, creating strong dipoles that tug on each other. But even if molecules are not polar at all, there can be electrostatic forces acting between them. How? Electrons move around inside the atoms, and by pure chance, they can end up on one side of the atom, creating a momentary dipole, which influences other particles next to it to become a dipole as well. At least for a very short time, as the electrons keep moving and the dipole disappears. This is called the van der Waals forces. The polarity of water also explains why it's one of the most versatile solvents to exist. It can pull apart molecules by tugging on charges, and it keeps them apart by surrounding a particle with its oppositely charged end. Water cannot dissolve nonpolar molecules though. It's the reason why water and oil don't mix, since fat molecules are nonpolar while water is polar. Just remember the ancient saying, similia similibus solventur. Or in the language that's actually spoken, similar things will dissolve similar things. Fun fact, soap works because the molecules that it's made from, which are called surfactants, have a polar head and a nonpolar tail. This way, when in water, they can surround, for example, nonpolar fat molecules and form micelles, which, along with the water, transport the dirt particles away. These are the most important bonds and forces ranked by strength: ionic bonds, covalent bonds, metallic bonds, hydrogen bonds, and van der Waals forces. There are three main states of matter: solid, liquid, and gas. Solids are tightly packed in fixed structures, where the particles can only wiggle. Unless, you smash them. In liquids, the particles can move freely but are still confined to a fixed volume, as the forces between them are still strong enough to keep them together, and the particles in gases have enough energy to just do whatever they want and fill up all the volume you give them. Knowing this, we can find two important words. Temperature is the average kinetic energy of particles in a system, or how much and how fast they move, and entropy is the amount of disorder. Substances tend to be solid at low temperature and or high pressure, which is a state of low entropy, as they're neatly organized and don't move that much, and gas at high temperature and or low pressure, where they move around like crazy, so it's a state of high entropy. Strong bonds, like ionic bonds, lead to high melting points, as they take a lot of energy and therefore a high temperature to break apart. That's why most salts are solid at room temperature, whereas water, which is only being held together by hydrogen bonds, is a liquid. Well, actually, there's another state called plasma, which is ionized gas and can exist at very high temperatures, such as in stars, or very high electric potential. The latter is used for neon lights. Gas is ionized in a tube with a very high voltage. Collisions of the ions with other particles makes their electrons move to a higher energy state. Once they fall back down, the difference in energy is released as light. The color of the light depends on the element that's used in the tube, as each element has different but fixed energy levels, and the difference between those determines the energy and therefore the frequency of the released light, which is what changes the color. All possible frequencies that an element can emit are called the emission spectrum. All matter can be divided into two categories: pure substances, which can consist of one element or one compound, and mixtures. Mixtures consist of at least two pure substances and can be homogeneous or heterogeneous. Homogeneous means the substances will mix evenly and the mixture looks the same everywhere, like salt and water, which is a solution. Heterogeneous mixtures look different depending on where you look. They have distinct regions made of separate substances. One example is sand and water, which is called a suspension. Okay, well, what about milk? That looks the same everywhere, so it must be homogeneous. No, milk is something we call a colloid, or more precisely, an emulsion. The difference between salt water and milk is that the solute doesn't fully dissolve in the solvent, meaning there are bigger particles than in a solution, but smaller particles than in a suspension. This allows the particles to stay evenly distributed but not fully dissolved, placing them somewhere between solutions and suspensions. Hey, remember sodium and water? What's going on there? Explosions are really just chemical reactions that release a lot of energy in a very short amount of time. Also, they expand, like, a lot. There's a couple types of chemical reactions: synthesis, decomposition, signal replacement, and double replacement. Here's an example for each one. They all happen mainly for one reason: to decrease energy and get to a more stable state. Chemical reactions happen in certain ratios. For example, to produce water molecules, you need twice the amount of hydrogen compared to oxygen. This is called stoichiometry. These ratios are based on the conservation of mass, which says that mass cannot be created or destroyed, only converted. Practically, when dealing with reaction equations, you have to make sure that there's the same amount of atoms on each side of the equation, and if not, balance it out element by element. As a rule of thumb, you should balance out the metals first, then the nonmetals, and then hydrogen and oxygen at the end. But it's really just trial and error until everything is balanced. Okay, but if you wanted to make this reaction happen in a lab, how would we know that we have exactly twice the amount of hydrogen compared to oxygen? You can't just take 10 grams of this and mix it with 20 grams of that, because the atoms don't weigh the same, so 10 grams of both contain a different amount of particles. What to do? Just look up the atomic mass of the reactants and take that amount in grams. You'll get exactly this amount of particles. That is 1 mole, which is just an amount of something, kind of like a dozen. In other words, we can interpret the reaction as 2 moles of this react with 1 mole of that, which we can easily measure. It's important to differentiate between physical and chemical changes, as reactions only take place in the latter. Physical change happens when the appearance changes but the substance does not. For example, hammering metal. A chemical change happens when the substances themselves change, and this is often accompanied by bubbles, a funky smell, or, you guessed it, explosions. All chemical reactions need activation energy to take place. Wood won't just spontaneously react with oxygen and start burning, or else, the planet would be on fire, but if you give it enough energy, it will. Catalysts reduce the activation energy needed for a reaction, which makes it happen easier and faster. And as a neat bonus, they don't even get used up during the reaction, so you can just reuse them. Because chemical reactions are changes in energy, it's quite useful to keep track of it. Enthalpy is, simply put, the internal energy or heat content of a system. If the total enthalpy of a reaction is lower at the end than at the beginning, heat was given off to the surroundings, which is an exothermic reaction. If it's the other way around, a reaction is endothermic. It's easy to see how exothermic reactions can be spontaneous. It's kind of like a ball on a hill. It will only start rolling if you push it a little bit, but then it will keep rolling on its own, just like wood keeps burning on its own. But in endothermic reactions, you have to keep putting in energy, like pushing a ball uphill. That doesn't just spontaneously happen, right? Well, yes, actually it does. To get the whole picture, we have to look at Gibbs free energy, which looks at the change of enthalpy, but also the entropy of a system, which is dependent on temperature. If this whole thing is less than 0, the reaction is exergonic, or spontaneous, because free energy was released. If it's bigger than 0, it's endergonic, or not spontaneous, because free energy was needed and absorbed. Here's where temperature and entropy come into play. Even if delta H is positive, so the reaction is endothermic, if the change in entropy is big enough, it can offset this and make the total free energy negative, which means the reaction is spontaneous. But this is strongly dependent on the temperature. For example, melting an ice cube is endothermic because it absorbs heat, but also it increases the entropy a lot as neatly organized ice turns into water, which is just kind of a mess. So this can happen spontaneously, but only if the temperature is above 0. If it's below 0, the water will spontaneously freeze, which is exothermic. If it's exactly 0, then no reaction will take place spontaneously. In other words, if delta G is 0, we're at equilibrium. Chemical equilibriums exist when reversible reactions take place at the same speed in both directions, which means that even if reactions are taking place, the concentrations of both sides stay the same, and to someone watching from the outside, nothing seems to be happening. We often find chemical equilibriums in phase changes, but also acid-base chemistry. According to Brønsted-Lowry, an acid is a molecule that donates protons, while bases accept protons. A proton in this case is just a hydrogen ion. So, with this definition, a molecule with at least one hydrogen that it can throw away can be an acid, and anything that can pick it up can be a base. This also means that once they react, they turn into the conjugate opposite, as an acid that gave away a proton can now accept one back, which is what bases do. A molecule that can act as both an acid and a base is amphoteric, for example water. A strong acid will dissociate almost completely into its ionic form, giving off a lot of protons to the water and therefore creating lots of hydronium ions. A weak acid just won't dissociate nearly as much, giving us a lower concentration of hydronium ions. So, to measure the strength of an acid, we can measure the concentration of hydronium ions. This is called the pH. Mathematically, it's defined as the negative log of the hydronium concentration, which means one step on the scale is a 10 times change, and also, since it's a negative log, the higher the concentration, the lower the pH. For example, pure water is in a chemical equilibrium. There's exactly one hydronium ion for every 10 million water molecules. In other words, the concentration of hydronium is 1 over 10 million, or 1 times 10 to the negative 7. Taking the negative log of this gives us a pH of 7, which is considered neutral. Anything lower than 7 is acidic, and anything above is basic, unlike you. You can do the same thing with hydroxide ions and you will get the POH, which keeps track of basicity. Fun fact, the pH and POH will always add up to 14 because they counteract each other, so by knowing one, you know both. Now, if you have a strong base and a strong acid and you pour them together, no, they will not explode, they will neutralize by forming water along with the salt, which is neutral. For example, hydrochloride and sodium hydroxide will form water and table salt. Oh yeah, speaking of table salt, remember how it consists of ionic bonds because sodium transfers an electron to chlorine? Well, that is called a reduction-oxidation reaction, or redox. If sodium chloride forms out of its pure elements, the sodium gets oxidized as it loses an electron and the chlorine gets reduced as it gains an electron. Logically, sodium is the oxidant and chlorine is the reductant. Of course not, that would make sense, it's the other way around. More accurately, redox reactions are reactions that change the oxidation numbers of elements, which are kind of like imaginary charges. There's just a few rules you have to know to figure those out. Hydrogen is mostly +1. Oxygen is mostly -2. Halogens are mostly -1. Single elements are always 0, and the number of all atoms in a molecule always have to add up to the molecule's charge. So this would total 0, while single ions just have their charge as the oxidation number. For example, in sulfuric acid, we have 4 oxygens, which totals -8. We have 2 hydrogens, which brings the total to -6. And since the whole molecule is neutral, sulfur must have an oxidation number of +6. Just by looking at the oxidation numbers of reactants and products, you can deduce the flow of electrons, which gives you these equations. If redox reactions happen in acidic or basic solutions, you can balance out the charges with ions and fix the stoichiometry with water. Okay, now to this weird looking thing. I spared you from it because for describing electrons, this is very simple and this is not. But this is actually like pretty wrong. Electrons don't orbit in circles. Here's how it actually works. All electrons inside an atom are described by 4 quantum numbers: n, l, ml, and ms. N corresponds to the shells, so all electrons with the same n are in the same shell. Within the shells, we have subshells with multiple orbitals, which are 3-dimensional regions in space where electrons could be. We know these exist thanks to Schrödinger's equation, which gives a probabilistic wave function. You can imagine it as a cloud, and the denser it is, the more likely an electron is to be there if we were to look for it. L describes the shape, and ML the orientation of orbitals in a subshell. There are 4 subshells called S, P, D, and F. If electrons have the same L, they're in the same subshell. If electrons have the same N, L, and ML, they're in the same orbital. Also, the number of orbitals increases by 2 for every bigger subshell, starting at just 1 for s. The last quantum number describes an intrinsic property of electrons called spin, which can have 2 values. Some guy named Pauli said 2 electrons can never have the exact same quantum numbers inside one atom. Since ms can only have 2 values, every orbital defined by n, l, and ml can hold a maximum of 2 electrons with opposite spin. Therefore, the s subshell can hold 2 electrons, the p subshell can hold 6, d can hold 10, and f can hold 14. Now, the quantum numbers restrain each other like this, which means that the first shell can only have an s subshell, the second can have an s and a p subshell, and so on. This means that the first shell can hold a total of 2 electrons, the second can hold 8, the third can hold 18, and generally the number of electrons a shell can hold follows the rule 2n squared, with n being the principal quantum number. The principal quantum number, and therefore the total number of shells, increases from top to bottom in the periodic table from 1 to 7. Every element has a different number of electrons that fill up these orbitals, and the different subshells and orbitals are filled in a specific order called the Aufbau principle. Just write down the subshells like this and draw diagonal lines from top right to bottom left. To get an electron configuration, just look up the number of electrons of the element in the periodic table and fill up the subshells in this order until there are no electrons left. This would be the electron configuration of sodium. You can also look up the next smallest noble gas and shorten it by just referring to its electron configuration as the base, because those shells are full and don't change for any bigger elements. This is also how you can figure out the valence electrons for transition metals. Just look up their electron configuration, ignore the full shells of the next smallest noble gas, and the remaining electrons are the valence electrons. Easy peasy. Anyways, all this knowledge is going to cost you 1 subscribe and a thumbs up. Thank you very much. Your comment is my delight, and I shall now guide you, fine person, to the exit where the next lesson is excitedly waiting for you.
This is a homeless Lego man. But today, I'm gonna build him a dream Lego house that only the most famous rich people could ever afford, adding different levels, expensive vehicles, and secret rooms. Then at the end, I'm gonna test it with natural disasters to see if it will survive. So anyway, let's go. Now, if we want this house to be massive, we need as much Lego as possible and as much space as possible. So I went ahead and bought as many Lego base plates as I could, and I'm gonna cover my entire table in them. Nice, and now that we have all this land to build on, we're ready to begin our house. So let's send in the first load of Lego bricks. Now the first thing we need to build is the entrance to this house. So I made this large driveway with a fountain in the middle, and at the very end is the first part of the house. So I built a security camera in case a robber shows up, and these 2 golden doors just to show how expensive this house will be when it's done. So once you enter, there's 3 empty doorways, and each one will eventually lead into its own special room that we're gonna add one by one. So first, let's begin with the bedroom, because after all, we sleep for 8 hours a day, which is 1/3 of our life. So I built a king-size bed, and behind it I built this expensive looking painting which looks like paint that's dripping down. I even built a giant TV so we can watch movies in bed. Okay, we have a place to sleep, but next we need a place to wash ourselves and crap. So my plan is to build the finest, most luxurious looking bathroom possible. So I built one with a golden bathtub, a large walk-in shower. I added this working mirror using a rare Lego piece. I used a round brick as a roll of toilet paper, and I even used a gun as a faucet for the sink. This homeless guy also needs better clothes because right now he has no drip. So next to the bathroom, I'm gonna build a giant walk-in closet where we can store only the most expensive, luxurious, high-quality clothing items, all the way from jackets and shirts to pants and shoes, different types of hats, and I even built different hairstyles that he can pick from. So now that he has all these new clothes, it's time to change his fit. Nice, now he looks like a millionaire. Next, I'm gonna build a Lego kitchen. And something that all rich people have is a private chef, because in the time they spend making food, they could probably afford a brand new Lamborghini. So I added a private chef, a pantry full of snacks and ingredients, and a working refrigerator with drawers and doors. And once the food is ready, we need a place to eat all of it. So I then built a dining room across from the kitchen with a giant table where all the food can be served. I built this special rug under the table by laying small pieces down on their side, and I even built this very expensive looking chandelier. Just this room alone is the size of an average house. The next room every house has is a living room. So I built one with a few couches, a map of Lego Earth. I even built this giant aquarium full of rocks, coral, and different sea animals. Hey, what are you doing? Go back to Bikini Bottom. Okay, now let's see if it can hold water. Oh crap, yeah, it's leaking, guys. But my favorite part of this room is the bookcase in the corner, which is actually a secret door into another room. Nice, that is so satisfying. And that means that now we can build a secret room that only the person living here could ever find. So behind the wall, I built a private museum full of rare precious items that are worth millions of dollars. Like this sword from an ancient Chinese battle, or this basketball that Michael Jordan used. You'll also find this very rare Lego minifig, this ancient artifact, and I even built an entire safe full of money. Okay, the first level is finished. But before we build the second floor, I'm gonna build a giant garage at the front of the house. That way we can fill it up with expensive cars. So inside you'll find a rack full of spare car parts in case one breaks, lots of tools so we can work on the cars, this racing trophy, and I even added a working garage door. And because this garage has so much space, the next thing we need to do is fill it up with fast, expensive luxury cars. So I built this McLaren, and I also built this Tesla Cybertruck. Now we're ready to build the second level of the house. So in this empty room we built from earlier, I built a giant staircase. But at this point, we're so rich that walking upstairs is a waste of time, energy, and therefore money. And that's for poor people. So I even built this house its own working elevator. Okay, so now that we've built stairs and an elevator, we're ready to begin the second level. Nice. Wow, we have a lot of space to build on, but my first plan is to build a dream gaming room, and I want to build one with the fastest, most expensive, high-quality gaming equipment. So I built this dual-screen gaming setup, and I even added a webcam and microphone. That way we can stream on Twitch, get donations, and get even richer. I also added this Spider-Man statue and different simulation games like this driving simulation and this VR simulation. Wow, this is every gamer's dream. Ninja would be jealous. My next idea is to build a Lego gym, because instead of driving to one like an NPC, let's just build one in our own house. That way we can work out whenever we want and have all the privacy we want. So I built lots of equipment, and I even built a small karate dojo with a mat to practice on and traditional weapons you can practice with. I also built some speakers to play music while we work out. This next idea is a huge flex, because what if we built an actual indoor go-kart track? But to build this, we're gonna need as much space as we can. So I built a giant room with a track that goes in a circle and a small go-kart to do laps. I built a rack for helmets, a stopwatch so we can record our lap times, and I even built this stoplight to tell us when to go. Okay, something I wish I had in my house is an indoor movie theater, so I'm gonna build one with everything that a regular movie theater in the real world would have. Like, I added reclinable chairs, different drinks and snacks you can have while watching, including popcorn, and finally, I built this giant fireplace with a TV above it. But to make it realistic, I added a background with minifigs, that way it looks like something's actually playing. Okay, I'm finished building rooms on the second level, but there's a giant balcony in the back, which means we have more space to build. So the first thing I'm gonna build is an outdoor basketball court. And the first thing we need to do are draw the lines of the court. I then built 2 basketball hoops and this rack full of basketballs, which means now it's time to lock in and get those buckets like LeBron. Let's go, he's the GOAT. No, like actually, he is literally a GOAT. For a more relaxing activity, I built my very own Lego mini golf course with 4 different levels you can play, each one offering a different challenge you have to complete. I even added spare clubs and extra balls to play with. I even built an outdoor trampoline park. With this trampoline I built using a net piece, and you can either decide to jump into this pool full of money since we're so rich, or if you're brave enough, you can jump off the literal balcony into this pool of water. Okay, the second level is finished, but we're not done yet because I'm gonna build one final level on the roof. So to build the roof, I'm gonna use a secret building technique where I build a giant wall in Lego, then lay it sideways. So let's go ahead and cover the entire house. Very nice. I even added some windows so we can look inside. My next plan is to give this house a pool, but since we're running low on space, I'm literally gonna build it on top of the house. So I built this giant, luxurious rooftop pool. It even comes with a slide, a container full of pool floaties, and these reclinable chairs. And while we relax, I even built my own butler, which can serve our Lego man drinks and massage his toes. And if that isn't relaxing enough, I even built this Lego man his very own personal helicopter. helicopter. That way now he can travel to any vacation spot he could possibly desire. Okay, that's the third final level of the house finished, but there's one final build I want to add. But before we do that, this house needs a better security system. So I went ahead and built a tall brick wall around the front of the house and this working gate that can open to let people in. I also built a small keypad so people can get in, and a highly trained security officer which can monitor who enters and leaves the property. And for the final, biggest upgrade to this house yet, I want to build this house its very own roller coaster. And because the entire backyard of the house is empty, it's gonna make the perfect place to put one. So I started by building a custom track which goes in a circle, a small cart to put our Lego man. Then I spent the next few hours building this small battery powered Lego device which rotates this tire and will propel the cart forward. Here we go. Oh, let's go. Oh my gosh, I feel like a genius. The cart is actually moving without me having to touch it. So now that we figured that part out, we can decorate the roller coaster and make it feel like a real theme park. So I went ahead and made a dinosaur themed roller coaster. I built a jungle full of different types of dinosaurs and a small lake in the middle for them to drink out of. Wow, our dream Lego house is finally complete. This Lego man really went from being homeless to having a better life than an average human. And to celebrate this house being finished, I'm gonna throw this house a giant Lego party. So I built a Lego clubhouse, and all invited guests can delight themselves in some free food and drinks, and a live concert hosted by Lego City's most famous music producer. I even built a security guard to only let the coolest, most famous rich people into the party. So we're ready to invite all the guests and get the party started.
Everything is awesome.
But we actually should have not celebrated too early, because what's the purpose of a house? To protect the people living in it. So I'm gonna simulate different natural disasters that would probably happen in the real world to see if this house is actually gonna survive or not. Starting with a windstorm. Okay, the helicopter got destroyed. Also, the gate blew over. But aside from that, this house basically survived. So for the final biggest test, I'm gonna simulate a giant tsunami. Oh my gosh, the flood was so powerful that it literally pushed the house back. As you can see, the entire driveway got destroyed and this roof moved, but the house actually stayed together. Comment how many booms you give this Lego house and what I should build next. Thanks for watching, I'll see you in the next one.
My heart's like a Lego set, please don't break it. I don't like mega blocks, please don't fake it. Everything is lit, yeah, everything is awesome. I build illegal tricks, yeah, and we never stop it.
In this video, I'm gonna attempt to transform this empty Lego building into a thriving shopping mall with a variety of stores, a food court, and more. Let's get started. Okay, so this shopping mall is gonna be rather large, and we have a lot of customers who are anxious to spend their money. Pretty much everybody likes candy, so let's start with a candy store. First, I'm gonna lay down a floor pattern, and to build the walls, I'll stack blue and lavender bricks to make this diagonal pattern for a cotton candy vibe. Obviously, the store is gonna sell some chocolate bars, fruit candies, and even some baked goods. Also, if you take one of these minifig paddles and stick this swirly piece on it, it looks like a jumbo-sized lollipop, and these energy pieces look like rock candy. To make this a special experience for shoppers, here's a station to make candy apples, as well as a cotton candy machine. And after some final touches, here's a cash register so customers can actually pay for all this candy. And for a store name, I really like Candyland from the board game, and it matches the store colors, so I'm just gonna use that. Okay, and it looks like our first store is complete. However, some of these shoppers have zero fashion, so we should probably make a clothing store. Not quite. I was thinking more like an Abercrombie & Fitch. Starting in the back, I'll add the cash register, and next to it will be a shelf with different perfumes and colognes. And on the other side is a selection of hats where I use these flower pieces to display them. Now as for the front of the store, I'm gonna build these shelves to split it in two sections. One for chicks and one for bros. And we can use those shelves to display shirts and tank tops. And for legwear, I built these double-decker racks for both sides. And I almost forgot, but no clothing store is complete without some display mannequins in the front window. And now that this place is open for business, our minifigs can pick out some fresh outfits. However, they still need a place to buy shoes, so that'll be our next move. Now, LEGO doesn't make any shoes for minifigures, so I used a bunch of small pieces to make custom designs. We've got Jordans, All-Stars, Crocs, Mischief boots, and even Heelys. I want this shoe store to have an old warehouse feel, so I tried making a floor that looked like cracked concrete. And for the walls, I'm gonna try something different and use these ratcheting hinge pieces to attach these large plates on their sides. This way we can use these bracket pieces as a shoe shelf. And to wrap this up, it makes sense to add a bench where people can try shoes on, and how about some wall-mounted speakers? Now, I don't have a name picked out for this store, so I just made this large custom shoe that'll go in place of the sign. That should get the idea across. And to complete the first row of shops, the ladies have requested a makeup and beauty store, so let's make a Sephora. These stores have black and white stripes on the floor and walls, so it's really important to feature that along with several beauty products, like this spinning shelf that holds cleansers, creams, and shampoo. LEGO also makes these hair clip pieces, so I modified the right wall to display some of them. Honestly, I don't really know what else to add, so I'm just gonna make a checkout counter with a few more products to tempt customers before they get rung up. And because the makeup industry is worth billions of dollars, we might need 2 cash registers. Come to think of it, a store that would pair well with Sephora is Pandora, the popular jewelry store chain. Now this store will be selling some very expensive items like rings, necklaces, charms, and other expensive jewelry. And because they're so expensive, I built 2 glass display cases to protect them. We'll put one on this back wall and one on this right wall. But now this corner looks absolutely hideous, so I made a really thin display to fill it in. Lastly, I'm using some clear bricks to make a glass counter where customers can check out. And it also doubles as a special display case for the most expensive jewelry. And that does it for Pandora. Oh snap, this place is totally getting robbed right now. And it looks like the crooks are making a run for it. This mall is in desperate need of security, and there's only one man for the job. Mall Cop. And I even built him his Segway. Thanks, Mall Cop. Now that the mall is secure, I'm dedicating this next store to the boys because it's gonna be a video game store. The best part is that it's gonna be 50% larger than a normal store, and I've got some plans for that extra space. I'm gonna go with purple walls for this one and add the checkout counter in the center. But this won't be much of a video game store without games, so here's a shelf full of them with some posters of hot new releases. But what good is a game without a system to play them on? So I built a bunch of video game consoles based on real life, and we can display them on this shelf that mounts to the back wall. But what good is a console without a controller? Well, I thought of that too and made this controller rack. And by the way, you guys remember Skylanders? Well, how about we throw some of those on a shelf too? And lastly, I'm gonna spruce up the floor with a rug that looks like a video game controller. Now as for that extra space, how cool would it be if this game store had a lounge area where customers could just hang out and try out different games? I'd say this is quite the level up from your average video game store, so I'll just name it that. Let me know if you would game here with the boys. But as awesome as this store turned out, video games aren't for everyone, and some people might prefer reading books instead. So I think a bookstore like Barnes & Noble is in order. But since Level Up was a larger store, this Barnes & Noble is gonna have to be a bit smaller, which might be a problem seeing as a Lego book takes up the entire entrance. So as a workaround, I'm gonna do my best to reconstruct this entire sidewall into a massive bookshelf. And here's another shelf with larger books to fill in this back corner. I think I can also squeeze in a reading sofa and a very tiny register at the front because that's all we really have space for. So hopefully the book readers are happy now. But if you're anything like me, fun activities like gaming or reading can't compare to building Lego. Now we've got a fully stocked Lego store. They even have that $800 Millennium Falcon set. And of course, we couldn't forget about the famous Pick-a-Brick wall and that Build-A-Minifig tower. And now that this Lego store is complete, so is the entire left side of the mall. And after all this shopping, I imagine our customers are getting a little hungry. So now's the perfect time to turn this middle section into the food court. I'm gonna build up this back wall and add these columns to divide it into 3 different spots. The first of which will be a Starbucks to keep these customers caffeinated. The front has some mugs you can purchase, and the back counter has some supplies and a coffee maker as well. That'll be $37. Next, I'm gonna put Chipotle in the middle. Right now, they're grilling up some chicken to refill the front counter where customers can choose what they want in their burrito. And finally, I'm gonna make a Baskin-Robbins so customers can get some dessert. The front counter is built out of these opening freezers with chocolate, strawberry, and vanilla ice cream inside. I also made signs for all these places, and we can probably use these brackets to attach them to this back wall. Yeah, that looks really nice. But I just realized customers still need a place to sit down and eat the food. So as a quick fix, I'm just gonna combine a bunch of plates together that can slip right under the food court, giving us an area to attach some tables and chairs on it. Okay, now the food court's complete. And while the adults are well nourished, these kids are all sugared up since they only ate ice cream and candy, and now they need a place to burn off energy, which is where this top section comes in because I want to turn it into one of those play areas. I'm gonna swap these gray plates with green ones so it has a more outdoorsy feel, and I'll add this lake area with a boat seesaw that can rock back and forth. In the front will be some colorful foam blocks the kids can climb on, and over here I'm gonna try to make one of those really fake looking trees, and I'll add a ladder for kids to climb to this top platform where they can use it to slide down the slide. And for some details, I'll add some pretend stones, a fence, and a bench where Karen can supervise from. Alright, nice. I think this play area will add a lot of life to the mall. Turning our attention back to the remaining shops, I want to try something a little out of the ordinary, like a medieval themed store. I could use a break from building though, so I hired a construction crew to do it for me. Thanks guys. Taking a closer look, the stone floor and brick wall really helps sell you on the whole medieval vibe, and this shop sells everything from handmade outfits to replicas of old weapons and a collection of shields. Pretty much anything you need in a medieval scenario. And just for fun, they even have a real-life horse you can feed. But speaking of animals, what if we built a pet store? Something like a Petco? That could be interesting. And there's a lot of animals I want to add, so it might get cramped. Obviously, we have to include spots for your typical dogs and cats. Next, I built this wooden bird cage with 2 birds inside that can hang from the ceiling. Fish are another popular pet, so here's a stack of fish tanks, and I put these blue bricks behind them to make it look like they're actually swimming in water. I'm also gonna make 3 different terrariums. One for turtles, one for a chameleon, and one for snakes. In addition, we should probably add some non-animal stuff, like a shelf with chew toys, a cash register, and this wall looks really bland, so I'm gonna hang this doghouse there, and now the store looks a little more complete. Wait, it looks like there's one more animal we forgot. And now we've arrived at the largest store in the entire mall, and I'm gonna attempt to turn it into a Dick's Sporting Goods. However, I'm pretty overwhelmed by the sheer size of this store, not to mention there are a lot of sports and activities I want to include. So as a solution, I divided the store into 3 main sections. This way I could just focus on one section at a time, which made this store way more manageable to build. This is actually coming out pretty good. And after spending some more time building, ladies and gentlemen, Dick's Sporting Goods is now open. How about a tour? This first section is dedicated to land sports like baseball, basketball, tennis. It even has fencing and cycling equipment too. In the water sports section are items like surfboards and fishing poles, and this final section is for winter sports like skiing and snowboarding. I should also mention that each section has a spinning display with specific gear and outfits related to that area of the store. Thank you for visiting Dick's Sporting Goods. Okay, we've approached the home stretch, but one thing every mall has that ours doesn't are some kiosks. So here's one that sells some delicious baked goods. This one sells a bunch of phone cases. I also made one of those old school looking popcorn stands. And here's one that's selling some cheap fragrances. Just be careful because they're pretty relentless when they want you to try a sample. Now that that's out of the way, I have a feeling this next store is going to bring in a lot of business because it's going to be an Apple store. Apple stores have a really simple design, so I'm going to leave the inside completely white, and I made these display tables full of Apple products like iPhones, iPads, Apple Watches, iMacs, and that's supposed to be an Apple Vision Pro. And yeah, I think that's pretty much it. We don't even need to include a cash register since Apple stores don't have them, but the employees will have to use a credit card reader because it looks like this guy just bought some AirPod Maxes to listen to a beat while we build a music store. Not only does this music store have a variety of instruments you can purchase, but it's also a place where you can just hang out and vibe, whether you're checking out the store's record collection or busting out some moves on the dance floor. And you may have noticed the stage in this back corner. Well, it's actually dedicated for karaoke. Okay, you're so good, we actually have to kick you out. Okay, so music isn't your best art, but maybe it's painting. So let's make a Michaels. Now to be fair, Michaels sells a lot more than just paint supplies. So in addition to canvases, easels, paints, and brushes, I'll throw in a bunch of other art supplies like glue, googly eyes, a sticker sheet, and a few slabs of clay. Alright, and that about does it for this store. And it looks like Bro is ready to redeem himself. Okay, we're down to the last and final store. However, after all this shopping, these customers look pretty tired and burnt out. So instead of a store, let's make them a spa. Here we have a lovely oak wood flooring, complemented by light blue walls with cloud details, as well as hanging plants for a natural yet calming atmosphere. At the front counter, you'll be greeted by Spamantha, our kind receptionist. She'll be happy to offer you a back massage with warm stones, a seat in the world's comfiest chair, or a dip in the jacuzzi to relax after a long day of shopping. Or crime fighting. Whatever it is you're tired from, I don't really care. And even though that was our last store, for a finishing touch, I want to add a centerpiece like a large fountain. And I'm going to combine a lightsaber blade and this blast piece to make a oddly realistic water spout. And I'll sprinkle in a few shiny studs to show any coins that people toss in. And I think our shopping mall is complete.
No watch, no diamonds, no watch, good timing, yeah. I'm sporty and rich, I'm sporty and rich.
Well, it looks like our work here is done. Now these minifigures have a place to spend all their money. Leave a comment and let me know what your favorite store was. Thanks for watching and I'll catch you on the next one.
We're now stranded on this deserted island in the middle of the ocean. And we're gonna be stranded here for the next 7 days.
What?
You're not Mr. Beast. And that boat that just left was our only way out of here.
So what do we do now?
I don't know.
We need to find some water.
Water? We're surrounded by water here.
He's not really gonna drink seawater, right?
Nah.
No, I don't think he will.
Are you serious, my brother?
Jay, I am flabbergasted by your stupidity.
Wow, it tastes a bit weird.
It's okay, guys. It's just a bit nothing to worry about.
There's a weird aftertaste.
Can somebody take care of him? We'll explore the island for a bit.
See you, chump.
Come on, man!
Wake up!
Sup, y'all?
Huh? Water!
Well, Jay is back now.
Yeah, I guess.
Don't you ever drink seawater again, Jay?
All right, relax.
And by the time the sun went down, we had everything figured out. Except one thing.
I think we should start the fire. Good idea, Cole. I got this!
Fire!
So the two most important steps to start a fire are having the right tools and the technique. That's why we brought some dried leaves, small branches, and some wood logs. Now,
If you smack two heavy balls together...
Whoa!
How did you do that?
Seriously?
I just told you.
All right, let's go to sleep. We got a big day tomorrow.
Good night, y'all.
Good night, Nia.
Good night, Nia. Good night, Cole.
Good night, everyone.
Good night, Zane. Good night, Jay.
Good night, Zane. Good night, Lloyd.
Good night, Jay.
Cole.
Good night, Lloyd. Good night, Zane.
Everyone, shut up!
Good night, Cole.
It took me a long time to sleep last night, and it went by so slowly.
Speaking of slow, where's Kai?
Hey, guys. Look what I found. It's a spear.
Yo, we could go fishing with it.
You'll probably need a boat then.
We found wood yesterday.
And I can build the raft.
Come on, let's go. You guys ain't coming? Sorry, but I don't like hurting animals.
Same here.
All right.
I don't mind hurting them. It was a joke. Ha ha.
after you, old cow! I caught one!
There!
Yeah, baby!
Another one!
Hey, yo, what's up, bro? Get back here, boy!
Zane, are you alright?
I'm okay, thank you.
I'd say that was a very successful day.
Yeah, I agree. I caught a fish.
What should we do today? We could build a shelter. Let's build sandcastles!
Oh yes, good idea.
Where's Zane?
He probably went to get the raft last night. I'm not sure. Actually, I don't know.
We can wait here for him to come back.
Let's do that.
Okay.
Cole, you cheated!
Zane isn't back.
Then we'll go find him.
Hey, where are you going?
We're gonna find Zane. We'll be right back.
Wait, I want to come too.
Wait.
This is where we found the water source.
Wow.
Well, Zane's not here.
Yeah, and it's gonna be nighttime really soon.
Already?
We could stay here and build a shelter.
Dude, Zane is missing, and you want to build a shelter now?
Yeah. We can go find him tomorrow. When it's daylight.
Fine, let's build that shelter.
Yes! Now we just need to make a fire.
I'll take care of the fire this time. Yes!
Guys, I think we forgot Jay.
No wonder it was so quiet.
We could go back to the beach and get him.
No, it's too dark, and you could get lost.
He's right. He'll be all right. Jay is a tough guy.
I can't believe they did that to me. They aren't even back yet. I guess it's just my imagination. All right, time to find Zane.
Yeah.
I guess we have two.
I have no friends.
Is that?
The same beach? Yes, it is.
Oh man, we've been turning around for an entire day.
Yeah, and my feet hurt.
And we didn't find Zane. Also, where's Jay?
He was supposed to be on the beach.
Let's head back to camp. Maybe he'll find us there.
Meanwhile, whatever happened to sticking together?
Man, I miss donuts.
We didn't find Zane. Jay is still missing. But you're thinking about donuts!
Hey, it's Jay.
Jay!
You guys aren't cool. I've been looking for you for almost 2 days.
We've been looking for you too.
We have?
I haven't slept. I'm really tired right now.
That's rough, buddy.
At least you found Zane, right?
We're working on it?
Well, that's just... It's Zane!
Zane!
Zane, don't you know it's dangerous to play with weapons? You almost destroyed...
Zane, what are you doing?
50-sheet auto-knock feeder!
He's unconscious.
Banana curtain 9.
Whoa! I gotta admit, that was a pretty cool move.
Wow, that was weird. I can't believe I lost to Zane.
Hurry up! Follow him, boys!
I'm not leaving you behind, sis. Let's go!
Later. Mr. Red's weather is greater than pudding.
Wow. Thank you very much, sir.
The treadmill was invented in 1818.
Yeah, boy.
I think I saw him go there.
Okay, I fight Zane's ice with my fire, and you two take care of Jay and Lloyd. Really? I can beat Zane.
Let's go with the first plan. I take care of Jay and you take care of Lloyd.
Fine. Nice, let's go. Not so fast!
Remember me. It's me, Lego Man. I saved you multiple times. I helped you when you were in trouble. But you never cared about me.
Hey! I could use a little hand.
I found this man a little disturbing.
And when I needed your help, you were never there for me. That's why I will destroy.
Do you guys understand what he's saying?
No. Not at all.
Hey, buddy. We don't understand what you're saying. Also, do we know you?
What did you do to Zane?
Hey, Kai! Catch!
I got you, homie.
We probably gonna need his blaster. Oh, right. Nia, throw the blaster! Thanks. How do you use this? I don't even know what I'm doing. Hey, it worked!
Hello, fellow teenager.
Zane, you're back!
What is on my back?
You guys might consider taking a bath. It doesn't smell that good.
All right! Jade, don't you dare drink seawater again!
Well, well, well. Students, congratulations. You've passed this test. Or did you? I'll be waiting for you in the dojo.
Wait, Master Wu, how do we go back?
Y'all can swim.
Well, thank you for watching this video. Don't forget to subscribe, like, and comment what you liked about it. Also, thank you for your patience because it took me a long time. If you want, you can join the Discord server. I've just set up an Amazon affiliate account, so if you need a certain Lego set, you can just go back there, and I'll get a commission. Every social media I use are listed in my Linktree page. Once again, thank you for your patience, and I'll see you in the next video. Peace.
What's the difference in Lego?
Attention all shoppers. We have a sale on all Lego items today. Hey, Lego's on sale. Legos are on sale. Hey, get out of the way. Excuse me, sir. What's the problem? We do have other brands. Sir, are you okay? Sir? Sir?